Hi, Anuj. I guess we can kickstart our section. We are good to go. The virtual
Okay,
ground is yours.
okay, fine. Yeah, good evening, everyone. Welcome to this session of DataHour series. Just a minute. Yes. Okay. So today we'll be going through the classification algorithm evaluation metrics, and we'll be studying about classification algorithms. What is classification? What are classification algorithms? And then the significance of evaluation metrics, followed by some of the hands-on also, right? So yes, a brief introduction about me. My name is Anuj Dhoundiyal. I'm a data scientist at IBM. I hold total 6.5 years of work experience. My area of expertise lies in machine learning, NLP, that is natural language processing, and deep learning. My hobbies are basically I travel a lot. So I love traveling, exploring new places, and having short acquaintances with new people so as to explore the place as well as learn something new from them. In addition to this, I love to do gym. I love to keep myself physically and mentally fit. That helps further in your life, right? So now coming back to the table of contents and what we'll be have going through today, we'll be going through the classification algorithm, some of the use case of classification algorithms, and then the evaluation metrics, then the classification algorithms, like what are the evaluation metrics, what is the significance of them, and then in classification algorithm, what evaluation metrics signifies, and we will going through each of them. So I hope it will be a more interactive session. I want you guys to keep putting down the questions, whatever you have. We'll be addressing the questions at the last. And I've tried to keep the content less, so I'll be talking more so as to keep it more interactive rather than just reading about the slide. So let's go with me. And I hope after this session, you will all be able to understand the evaluation metrics and what is classification, everything related to that. So yes, let's get started then. So coming to the classification algorithm, now we try to understand like what is machine learning. Yes, we are like some of you should already know about like what is machine learning, but if somebody doesn't know, so basically machine learning is actually studying from the historical data and trying to actually mimic the human behavior, right? So we have the historical data. So machine tries to understand the historical data, derive patterns from it, and then in order to frame down a model so that that model can actually serve for the future, right? So any in future incoming data point is there, it tries to predict it, right? So in machine learning, which is a subset of AI, we have two type of learning, right? One is supervised and other is unsupervised. Now there are two types, the supervised and unsupervised. Now supervised learning completely like plays with the label data. Now, what I mean by label data. So label data is as easy as like you can easily understand that, right? You have a fruit of baskets, right? You already know like what is banana, what is grapes, what is mango, right? So there are certain features which actually help you to determine that, okay, this is a banana and this will be an apple or this will be a grape, right? So we, and in the same sense, we have a historical data where it is exactly labeled. So just try to see that if there are four features, like feature one, feature two, feature three, and feature four, right? So there are four features, and there is a one column called as label, or you can say as category. So we know that on the basis of this feature, it has been labeled as a following fruit, right? So this is an example of basically a labeled data. Now coming back to the unlabeled data. So unlabeled data for the same problem statement, if you have the features but you doesn't have the labels, right? You have features, okay, these are the four features, but it's not given to you that, okay, this will be a fruit, this will be this type of fruit, right? Whether it be a mango or banana. So what those algorithms try to do, so basically supervised learning, we actually all of the algorithms use this labeled data, and unsupervised learning, we use the unlabeled data. So today we'll be going into one subset of machine learning that will be called supervised. Now, inside supervised learning also, there are two types of algorithms. We say as classification and regression, right? So in this also, we'll be going today through classification because all are very broader level topics, right? So we have tried to actually focus on one so that we can easily try to understand it. So coming back to the classification. Now, what exactly is classification? Basically, classification algorithms are which are used to actually identify the category, or you can say the label of new observation, right? So we can say about any example. We have a label data, just as we told, we have a fruit of baskets, right? And we have a whole lot of historical data. Now, in the future, if any fruit is there, on the basis of those featured, it will automatically classify whether it will be fruit A or fruit B. So in that easy sense is a classification algorithm, how they work. Now, what does classification algorithm do? It actually learns from the data or whatever historical data. That's why we say that for machine learning, actually data is very important. Just because it should not be any kind of data, right? The data should form any significance to the problem statement you are trying to solve. So these classes, whatever you say, are actually it can be termed as anything, be it a target, label, or categories, right? Now, classification algorithms, there are two types basically. In this also we have two types. One is called binary and other is called multi-class. Now, binary can be when your label or your category are two, right? What I mean by two, it's exactly whether you are, if you're trying to solve a problem statement such as whether a given email will be spam or not spam, right? It's a common use case. We all use Google, Yahoo, or other mailing systems, and it has a category called spam. Now, what the mail system does is, on the back end, there will be some model running, or they have any kind of model that is basically working behind that. But what it tries to do is it tries to classify any mail if it is a spam or not. If it is not a spam, it lands in your inbox. If it is a spam, it goes directly into the spam folder, right? So this is an example of a binary classification, or you can say a binary classifier working, where it has two labels to deal with. Now, suppose you have more than two, right? Just as taking an example of just a sentiment analysis, or you can say you have movie reviews, right? Now, it can be a positive review, it can be a very negative review, as well as it can be a neutral review, right? It's not that much positive, or it was not that much negative also. So this is a typical example of more than two class. Now, there will be three classes, right? Whatever historical data would be there, it will be mapped to three classes. One is positive, one is negative, and other is neutral. So we term this as multi-class classification, right? A multi-class classifier where exactly more than two classes are there in your data, and for any future data, you will try to predict the right class among those three classes, or exactly more than two classes. So anything more than two classes, it terms as multi-class, right? And two classes, we have binary, right? It's as easy as this, like classification algorithms. Now we got it. What is classification algorithm? From where does it comes in the machine learning hierarchy? And inside the classification, what exactly works and what are the types, right? Now, going back to the example of a binary classification, right? So suppose there are two features, X and Y, right? I plotted those features. X, there is a feature one on X axis, there is a feature two on Y axis. Now, on the basis of those two features, there is a historical data that already has the label. As I said that for classification, we need label data. So this is also a label data, right? So for few of the data points, it's termed as it will be a class A. For few other data points, it should be class B. So now there is something, or there are certain patterns or properties for those features which actually help you determining whether it is a class A or class B. So what classification model does is, whenever you are trying to train any classifier model, it actually derive those relationships, or you can say derive those patterns in order to quantify, okay, if any future label or future point will come, whether I will drop it into the class A or class B, whether it will classify it as class A or class B. So this is a typical example of binary classifier. Extending the same to it, if there will be one more class, then in this data set only you can consider there will be a feature one on X axis, feature two on Y axis, same, and there will be one more class called class C. So there can be one more horizontal or vertical line in order to determine those points as class C. So if it is class A, class B, or class C, as I said, more than two classes, it will be multi-class classifier, right? As easy as that. What is binary, what is multi-class? Now coming back to the classification algorithm. So in machine learning, as you already be aware, if somebody is not aware, we have various algorithms that are there. So each algorithm has a statistical implementation. We can actually code them from the scratch, or their machine Python. In Python, we have a very rich source of library set such as sklearn, which actually provides you the whole implementation inside a single function. But it's not like you can exactly directly use that. You need to understand the significance of algorithms. Now, some of the algorithms which are quite famous, or you can say which are quite basic whenever you try to learn data science or machine learning, that are logistic regression, support vector machines, naive Bayes, decision tree, and random forest. So these all are classification algorithms which actually helps you to, in order to have your data, have your historical data, and then okay, 1 minute. Yes, have your historical data and then trying to determine, okay, what will be the whatever future data point will come, whether it will be class A, class B, whatever was in your historical data. So now you can understand what is the significance of the data. That data should be more, that data should be important or pertaining to your problem statement you are trying to solve, right? Whether you are trying to solve a problem statement of whether a mail will be spam or not, right? So all of the data that you need which should be with respect to spam and not spam, so that it can actually help you derive relationships, and the model can actually serve as a perfect model for your future data, right? So for each of the algorithm, there is certainly an input format you need to actually provide the data in. So certain algorithms, each and every algorithm has certain different input format. Yet, right? There are features, so you need to scale those features. So directly also you can apply them, but what are the guidelines, or what is the appropriate method to use those algorithms? Is you, for some of the algorithm, you need to scale down the features. You need to provide the features into the range of 0 to 1, or normalization or standardization. These are the basic feature processing techniques that you need to follow for any algorithm to apply. So as model is trained on a historical data, so it can easily do the prediction for any of the future data, right? This was all about classification algorithms. Yes, now coming to the some of the use cases. No, some of the use cases that I've already talked up till now, but we will try to understand them once more, or if anybody hasn't gone through till now, we'll try to explain one more time, right? So first is an email spam detection. So it is a typical case of what you say, a binary classification, right? Because a certain email can be spam or it cannot be spam, right? So as we already discussed, right, in Yahoo Mail or Gmail, your mail comes, it automatically get classified as whether the mail will be spam or not, right? So it is an example of a binary classification, right? Now, second is the drug classification, right? So drugs classification is also an example of a binary classification only, where we actually try to classify whether this drug will be effective or not. So, right, so your problem statement says that, okay, these are the list of drugs, and whether this drug will be suitable, or whether the drug will be effective or not. So this is an example of a binary classification again, where whether we are trying to classify, okay, our drug will be okay, good enough for this or not, right? Third comes sentiment. As I talked about, sentiment can be positive, negative, or neutral, right? So it sometimes it can be a binary also, whether we are trying to classify it will be positive or negative. But sometimes if we have a historical data that suggests that, okay, there are some of the reviews of the movies where some of the comments are neutral, right? They do not say the movie is quite good, but they do not also say the movie is quite bad, right? So neutral kind of review. So it can also serve as an example of multi-class classification, but it completely depends upon the data you have, right? The movie reviews data set. Now, coming back to the fourth example of a use case, image classification. Now, this is a common classification which all have heard about. There are images, and we are trying to classify, okay, what are those images? So there are certain data sets that are available in UCI repository, or any, you can easily Google it. There are various classification data sets that are open sourcely available for you to practice, right? So there is image classification data set also. It has certain kind of images, right? So we will take a subset of that example. So let's try to understand whether in a folder there is a historical data that says there are images of 3 species, right? We can say one is whether the image will be cat or not, whether the image will be a dog or not, and third, you can say whether the image will be a monkey or not, right? So there are 3 images: cat, as I told about cat, monkey, and the third will be Third, you can consider anyone. I just forgot what I said. So there are three kind of images, right? We can say, or easily you can take it as image one, image two, and image three, right? Now, this you have a whole lot of historical data that is actually labeled. Okay, I'm providing this image. This is a cat image. This is a dog image, and this is a monkey image, right? Now you need to train a model, or you need to train your classifier in such a way that if any future image will come, you can automatically classify, okay, this is a dog image or this is a cat image. So this is how it works. Now this is also an example of multi-class, more than two classes. So images can be many. So as more as the data you have pertaining to the images or the category of the class, the better would be your model you would be training on that. So these were the few use cases where actually we apply classification algorithm, and this is the beauty, right? You need to understand the problem statement. Whenever you get a problem statement in machine learning, you need to understand what kind of features are, okay, what labels it has, how many labels it has. Then you can understand that whether this is a classification algorithm use case, and inside that, whether it's a binary classification use case or a multi-class. So this is how it works. You need to, that's why it's said it's very important to understand the problem statement and to understand the historical data associated to it, so that you can directly apply the correct classification algorithm, any algorithm you can choose. Or if you are actually applying multiple algorithms, then you need to understand which algorithm is actually serving your use case. That comes, here comes the importance of evaluation metrics, right? So we'll be moving to the main section where we'll be trying to understand what are the evaluation metrics of the classification algorithms, right? So first, let's go to the evaluation metrics. Now, evaluation metrics, what are they? Why are they so important? Now, evaluation metrics, from the name it suggests, right? Uh, Trying to evaluate something or trying to justify something, right? Trying to say that, okay, why it is important or how good it is, right? In the similar way, evaluation metrics for any algorithm works in the same way, I can say. You can say, if there is an evaluation matrix, it will, 1 minute. Okay, actually this okay, this poll, just a minute, guys. I'm not able to actually minimize this poll. Yeah, okay. So evaluation metric exactly is used to measure the quality of statistical or machine learning model. So measure the quality means, okay, you have trained a machine learning model or a classification model or given data set. Now, how good it is, you need to determine, right? You cannot directly train a model to say that this will be the perfect model, right? There should be some metric supporting it, that, okay, how good was my model? So this is the actually the role of evaluation metrics, and that's why the key role of any evaluation metrics in classification or in any algorithm is to justify, to actually tell you the quality of your model. Okay, if you need to further fine tune your model, if you need to further change the parameter in such a way that your model can actually be good to your data, whatever data you provided. So it has various significance, right? First, defines the algorithm performance or behavior, right? So it can actually defines, okay, how your algorithm is performing on your data set, right? Then it helps you decide the best model. So suppose there is a problem statement of same problem statement, classifying the mail as spam or not spam, right? You train three machine learning algorithm. One is logistic regression, second is a support vector classifier, and third is naive Bayes. Now, you've trained the three, and three are working fine, but you need to understand, right? For my data set, whatever I've trained, and for any new data set, for new unseen data, you say that any of the new data point that comes in, which algorithm would actually serve my purpose, right? It should be like any algorithm, or in fact, if three of the algorithms are serving good, then it is quite good. But if you need to pick down one for your production deployment, right, you need to understand which will be the best algorithm for me. So here, evaluation metric will play a key role. And third is also, it can help you parameterize the model. So how it helps, basically, when you figure out the evaluation metrics, and suppose the metrics are not good, right? So you can so every algorithm has certain parameters. So you can fine tune those parameters, or you can play more with those parameters in such a way that, okay, next time the algorithm's model is trained, it is actually performing better, or that metrics improve it. So suppose there is a metric called X, right? I'm not actually naming the metric. There is a metric called X. It is actually coming down as 70%, right? So 70% is actually good, but you actually know that it can actually be better, right? It can serve more, your algorithm can serve more to your data. So you fine tune your parameter in such a way that at 70, try to increase that to 80. And now 80% is a very good accuracy for any model, right? So in the similar way, you move forward. So it can also help you parameterize the model. So now coming to the classification algorithm evaluation metrics. So going down deeper into what are the evaluation metrics. So today we'll be discussing about three key evaluation metrics of any classification algorithm. First is the confusion matrix, second is the AUC ROC curve, and third is the log loss, or you term it as a cross entropy loss. So these three are the evaluation metrics that actually can help you to evaluate any classifier algorithm you have in your system, right? If you are training down any classification algorithm, it can actually help you serve, okay, like this is the perfect algorithm for my use case. So we'll be understanding each and every algorithm, and then going down into some of the hands-on also, right? Any algorithm, I say, okay, how to generate those metrics, right? So basically we'll be having a display of those metrics and trying to understand that, right? So we'll be going slower. I hope that till now the content is consumable and everybody knows about classification algorithms and what is the importance of evaluation metrics, right? Now coming to the main part, like what are those evaluation metrics? So as the name suggests, right, the confusion metric. So it's quite funny, right? The name is also the confusion matrix, and people say that it's quite confusing. It is confusing, but if you're trying to understand in a better way, or if you have understood it in a correct way, then nothing is nothing. You will not get confused, and each and everything inside this confusion matrix, you will be able to summarize it, right? So I've drawn this on the left hand side. You can see this is called a confusion metric. Now, how exactly it is prepared? We'll be going through every bit of it. Now, trying to understand what is a confusion metric. So it is actually a summary of your prediction results on a classification problem. So how to actually justify it, whenever you have any machine learning data set and you are training any classifier model, then you divide the data into training and test set, right? Why divide the data? So that for some of the data, I'll be training my model, but I need some of the data so that I can evaluate my model. Now, here comes the importance of evaluating your model. So you need the test data in actually to determine, okay, here was my model that was not trained on the data because I've separated this data out, but it was from the same domain only, right? I've picked out a subset of the data and kept it as a separate entity. Now, how my model will actually perform on this data. So this is the key behind any evaluating your classifier model or seeing any evaluation metric. So in the similar way, what we do, we prepare a model and then we actually summarize that model on a test data, or we see the prediction result. So now going to this confusion metric. So let me all of the students or working professionals who have joined the session, we will try to understand the confusion metric. So I would like everybody to go with me only. Like first trying to understand the ISJ, like value at one I and one J, right? Any matrix or you say the rows or column, you justify the values of I and J. So you can understand that 1 1 also, or 0 0. That will be perfect, right? 0 1 and 0 1, right? So first value is a true positive, right? TP. True positive. Now, what exactly does true positive mean? Suppose you have a model, right? And you, as I told you, divide your data set into training and test set. Now, you are summarizing your model on a prediction, right? Actually on a test data in order to evaluate your prediction. So these all will be the numerical figures. These are numerical figures, right? Whether it will be or not, right? Now, true positive says in my actual data, this data sample was positive, right? So we have two classes. I'm considering positive or negative, right? You can consider anything, spam or not spam. Positive and negatives are quite easy to understand. Confusion matrix, I would say. That's why I've taken positive, negative. So your data set says there are two classes, positive and negative. Now try to understand first thing, true positive. In my actual data, the data point was positive. And now coming to the column value, right? Your model also predicted it as positive. Now it's a win-win situation for me, right? My model is very good. Whatever data I had was a positive example, and my model also predicted down it as positive. So it's perfect, right? True positive, true. That's why it's called true positive, right? predicted also true and true in reality also. So if I consider it as an example of spam, right? My email was spam and model also predicted it as spam. It's perfect situation. That is called a true positive. Now the true positive would be a number. So suppose you have 10 data points in your prediction, right? Out of those 10 data points, there were 4 positive and 6 negative. So out of all the 4 positives that were, that were actually positive, just because it is a test data, you have that label data in hand, right? For any prediction data point that will come out in the future, you won't know it, but that's why you evaluate a model, right? So true positive in actual also it was positive, and the model also predicted down as positive. That's perfect, right? True positive. Now, just in the diagonal, come down to true negative. My data set says this data point is negative, and my model also predicted down it as negative. Now, again, in actual also it was negative. My model also predicted down it as negative. Again, a win situation for me, right? It's perfect. My model is doing good on that data, right? So it is called true negative. That's why true positive, true negative. So these two are the main entities that actually define the correct behavior of your model, right? In actual true, model also predicted true. In actual false, model also predicted false. So these are the two perfect things, true positive and true negative. Now coming down to the false positive, right? So it is false positive. So something is wrong or something is there, right? As the name suggests, false positive, right? In actual, the data point was negative, right? So my email was not spam, but what my model did, it actually classified it as spam. That is wrong, right? Your data point is not spam, and your model is saying it as spam, right? So this is something not good, right? So that's why it's called false positive, right? It is a positive that your model predicted down it as positive, but it's a false prediction, right? That's why we term it as false positive. So your in actual data it is negative, and your model predicted down it as positive. So same thing, false positive. That's why I named as false positive. Guys, it is very important, because on the basis of these true positive, true negative, false positive, and false negative, all the metrics would be derived. So I want you to actually focus on this and trying to understand this, right? So we are quite familiar with now with false positive. So that's why it's an error, right? It's an error, in your prediction. So that's why a false positive is also called error one, or you can say error, right? Error one, right? In the whole metric. Now coming back to the error two, there are two kinds of error, error one and error two. First error we have tried to understand, that is false positive. Now false negative. In my actual data, the data point was marked down as positive. Okay. But my model predicted it as negative. So coming to the example of spam mails, okay, this mail was spam. I know that because it is a label data. It is the training data, part of a training data, the test data. But my model said it is not a spam. So this is something error that model is doing, right? It is not doing good to that data point. So that is called false negative. Model is predicting it as negative, but that is a false prediction, right? So attaching false to it, false negative. So it's as easy to understand now. What is true positive, true negative, false positive, and false negative. So in this, true positive and true negative are the perfect kind of prediction that is model is doing. And the two kinds of errors are false positive and false negative. So now on the basis of these four entities, right, guys, in the confusion matrix, there are four kind of matrices that are actually can be derived for any classification algorithm. So these four matrices, we'll try to understand what is the significance of them, why they are termed it as the following names, and then how can you imply down in your actual classification use case, right? So first is accuracy. Now, I guess accuracy everybody is aware about. Like we every now and then we say if any system is there, how accurate it would be, right? We have all studied from our class 10th or class 12 standard, right? If a system is doing okay, what is the accuracy of your system, right? How accurate is your system? But in terms of confusion metrics, how we imply it down, there are certain formulas. I have not written down the formulas, but we'll be going through each and every formula. That's the beauty of this, because I don't want every mathematics things to be involved here. I want you guys to understand in terms of practical use cases, right? So accuracy is again an evaluation metric for classification problem. It's the number of correct prediction made as a ratio of all the predictions. So this is very important. First, go by the line number of correct predictions. Now, Going back to the previous confusion matrix, what are the correct prediction, guys, here? As I told you, what were the correct predictions, right? You can actually type down, but I need to know from you, what are the correct predictions here? True positive and true negative, right? These were the correct, right? An actual positive predicted positive, actual negative predicted negative. So these were the perfect kind of prediction. So what accuracy does is it takes the numerator as true positive and true negative sum, and it divides down into total number of samples. So what will be the total number of samples here? True positive plus true negative plus false positive plus false negative. So sum of the whole matrix will be the denominator. So what will the formula of accuracy? As easy as that. True positive plus true negative divided by true positive, true negative, false negative sum. So this is the accuracy. How good is my system? Okay, my system made these amount of correct predictions, and these were the total predictions. So suppose you have a data set, you have a test data set of 100 data points, right? It actually works down it as your there were two positive as 40, and now there will be integer figures, right? 40 predictions were actually positive, more were also predicted positive, and 40 were true negative, and 10 were false positive, 10 were false negative. As easy as that. So what will be your accuracy? 40, that is a true positive, plus that will true negative were 40 again, right? 80 divided by 40 plus 40 plus 10 plus 10. As easy as that. 80 upon 100, that is 80%. Okay, my model is 80% accurate. That is quite good accuracy, right? So this is the one kind of metric that can actually help you. We'll try to understand the significance of going further into them, but now just understand what is the significance. Like now coming to the precision. How precise is my system? It is exactly defined by ratio of correctly classified positive samples to the total number of classified positive samples. So by the statement only, you can actually understand it is completely dealing with classified. It is completely dealing with predicted data points, right? What is the prediction? How good is the prediction with relation to the positive samples? No. Coming back to the previous slide again. Here, what will be the precision formula, guys? Ratio of correctly classified positive samples. Now, here, what is correctly classified positive samples? It is again true positive, right? So my numerator will be true positive. Now I know in actually trying to derive the formula for precision, we know that true positive is in numerator. Why? Because we have to take the correctly classified positive samples. Ratio of this to the total number of classified positive samples. Now, in this, what is the total number of classified positive samples? Just see the column 1, guys. It is exactly the total number of predicted positive, right? And what is that? True positive plus false positive, right? What it is saying, okay, what I am saying, out of all the positives predicted, how many were correct? This is exactly the precision. Now, as easy as going with the definition, we can actually imply them in the practical knowledge. Out of all the predicted positive by my model, how many were them correct, right? So this is your, this tells you about how good is the model in terms of precision, like what is the precision of your model. Here, till here, everything should be clear, guys, I guess, because it is as easy. You can try to understand true positive plus true positive or false positive. In practical sense, whatever my model is predicting down it as positive, how many were actual positive, right? Now, coming to recall. Recall is again an evaluation metric that is associated with classification algorithms, but trying to understand it as in the form of formula that says number of positive samples correctly classified. It's the same, right? In precision also it was saying the number of correctly classified positive samples. So the numerator becomes true positive here, right? Now what will be the denominator recall? The ratio between number of positive samples correctly classified as positive to the total number of positive samples. So it is now here, it is not saying total number of classified positive sample. It is saying the total number of positive samples. That means in my actual data, how many were positive? Out of that, my model predicted how many positive. Okay, so precision says dealing with the predicted results. Recall says, okay, in my actual data, if 100 were positive, how many my model was able to classify them as correctly positive. So recall formula is true positive divided by true positive plus false negative. So it's easy, but in order to digest it as why precision and recall came into the system, I'll be telling you, explaining you by each of the use cases, right? I want you to understand in terms of use cases why precision is there, why recall is there, why to consider that. But as of now, you should be clear about the formula. A recall is in my actual data, out of my actual data, whatever were the positive, how many my model classified down it as positive, right? Now coming to the F1 score. F1 score says, okay, let's combine precision and recall, which because in actual sense, when we be going further, precision is also an important metric and recall is also an important metric, right? So my F1 score says, let's combine precision and recall in a sense that it will be a harmonic mean. So now harmonic mean is actually the average of reciprocals, if we will be understanding the mathematical sense. So 1 by P plus 1 by R divided by 2. So completely the final formula will come down as 2 into precision into recall divided by precision plus recall. So we'll try to understand why it is harmonic mean, why not average, right? Because the first question comes, why not simply averaging? Because it needs to be a combination of precision and recall. So let's try to combine precision and recall and do the average, right? But we are trying harmonic mean. Why? I will come down to this point by harmonic mean. But now let's try to understand in the use case sense, because whenever your classification algorithm matrices are there, it becomes very important to understand why when you need to consider accuracy, precision, recall, or F1 score. Now let's come to a problem statement of whether your algorithm is doing spam or not spam classification, right? And understanding in terms of why certain accuracies actually sometimes an important metric, but sometimes it becomes not a metric to observe, right? So suppose you have a data set, right? The plane will land safely or the plane will crash. Okay, now my first class says plane has landed safely, and second class says my plane crashed. You have 1,000 data points. Let's try to make it more smaller. 100 data points. 90 says my plane will land safely, and 10 says my plane will crash. So you know that your data set, what I mean by this data set problem is it's a unbalanced data, because balanced data says for every label there should be enough data points, right? But for this, for crash I have only 10, but for safe landing I have 90. But this type of problem statement are in real, in practical scenarios, guys. We do not have sufficient data for each of the label, right? That's why we say that uh, in quite many use cases you have unbalanced data, right? So if you have this kind of data, let's suppose you're trying to calculate accuracy of a system. So for say out of 90 sample, it has classified every 90 as it will land safely, because the machine learning model has learned perfectly, right? So the true positive 90. But out of those 10 that crashed, your model is not able to predict those 10 because the positive class is so much, because your positive class is a major class here in unbalanced data, right? Here comes the problem. So even if your true positive is 90 and your true negative is somewhat a lesser figure, still your accuracy will be very good, right? So now because your accuracy say true positive plus true negative upon the whole sum, still your accuracy is 90%. But is it justifying your problem statement? It is doing good with one class, but it is actually a biased class. But it is not doing good or justice to the second class. Still your accuracy is 90%. So you will say that, okay, it is a very good model, but it will not perform good. So that's why we say, if we have balanced data, then classification, then accuracy can be considered as a good metrics. But if your data set is highly unbalanced, or is you have an unbalanced data, that is more in real life you have unbalanced data set, then accuracy cannot be considered, right? Now I hope that accuracy now everybody knows. Now coming to the precision, why in certain use cases you need to choose. So precision recall and F1 score, guys, coming to the precision and recall, you need to choose one out of them, right? Or you can either, according to your problem statement, you can choose the combination of two, such as an F1 score measure, right? But in certain problem statement or use cases, there will be important to see, okay, whether I need to consider precision or recall that is actually justifying my problem statement. Now, just having an example of spam mails, right? My mail will be spam or not. Now here, just see, in a use case of spam classification, what you do, if my mail will not be spam, and your algorithm says it is a spam, then your mail will actually, that the mail that is important to you will actually land up in a spam folder. Now that is a worst use case, right? Because there was an important mail that came, and that was actually a spam, but your algorithm classified it as the mail was actually in your real data set. Coming back to your real data set, guys, a real data set says whether the mail will be spam or not. Now in precision, we know that it's a formula of true positive upon true positive plus false positive. You have to minimize the false positive anyway. You have to minimize the false positive so a precision can be higher for your system. So whenever the false positive or the cost of false positive is more, you need to minimize that. There you need to consider precision as a problem statement, or I would say as a metrics, right? In order to choose down a certain metric, if you want to choose down precision, then you need to understand what is important. You need to minimize false positive or false negative, because if you're trying to optimize or trying to reduce false positive and false negative, they go in certain number. If you're trying to increase the precision, the recall will go down. If you're trying to increase the recall, the precision will go down. That's why we say there is a certain trade-off between those two, right? And now coming to the example of recall, right? Recall is a metric which says true positive upon true positive plus false negative. You have to minimize your. So uh, here the false negative, I would say, is actually, it is stated as false negative is a crime, right? So consider an example of cancer treatment, right? Whether the person has a cancer or not. Now consider in your actual data the person has a cancer, but your model predicted it as the person does not have a cancer. Now, this is a crime, right? Your false negative is a crime here. If the person has a cancer, your model should tell that person is actually having a cancer. If your model is not telling that person does not have a cancer, if your model is telling that, okay, this person does not have a cancer, he will not actually do certain medical treatment, and which can actually cost his life, right? So that is why your false negative such a major role. Your false negative needs to be less, because the false positive can be more here in the use case. Just try to understand. If your person is not diagnosed with a cancer, in actual data, the person does not have a cancer, but your algorithm says it has a cancer. So he can certainly do more medical tests and try to prove that, okay, this was a false result. But for, like, out of choosing between false negative and false positive, you need to understand which one costs more to you. Now in the cancer problem statement, false negative is a crime, but in email we saw that, okay, false positive is actually a crime there, because uh, the mail is not a spam, but your model predicted it as a spam mail. So if it is a certain recruitment mail, right, and it happens on Gmail sometimes, you guys must have seen that it's a certain recruitment mail, and that automatically gets classified due to some algorithm, whatever working the backend, but it is not majority use cases. It happens sometimes that mail is classified as spam, and as it automatically goes into your spam folder, so we all have a tendency to look the inbox folder and ignore the spam, right? So their precision is a key metrics, but in the cancer problem statement, recall is a key metric. And now coming to the F1 score, F1 score says, let's combine harmonic mean of precision and recall, right? 2PR upon P plus R, as simple as that. But trying to understand F1 score in the sense that, okay, my F1 score is, why my F1 score becomes important. In certain use cases, you need to actually understand the significance of precision and recall both. You cannot compromise on either on false positive also or false negative also. There we consider F1 score as the perfect metrics for our problem statement. Okay, so F1 score when you are trying to consider precision and recall. And now I coming back to why harmonic mean, guys. So suppose your precision is 1 and recall is 0. Now your model is very bad. But if I would have taken an average, it would have been 1 plus 0 by 2. It would have been 0.5. Still, it looks your model is good. But in actually, your model is doing a blunder. It has a recall of 0. That's why it's defined as a harmonic mean, because harmonic mean actually in mathematics, it punishes the extreme figures, right? If your recall is 0, your F1 score becomes directly 0, right? As easy, even if your precision is 1. That's why we have taken a harmonic mean of in F1 score calculation, right? Uh, Hands-on we will do it the last. Let's try to understand the second metric, that is AUC ROC curve. Now, AUC is area under the curve. Which curve? ROC curve. So area under the ROC curve. ROC is receiver operating characteristics curve. So this is actually again one more metric in your classification algorithm which you can use. It's actually this complete matrix works on your probabilities, right? So whenever you are doing classification, you try to classify it as yes or no. But in machine learning or in statistics, there are probabilities, right? And on the basis of those probabilities, you define it as 1 or 0, as easy as that. Okay. So now your probability, the manual threshold of probability is taken as 0.5. You can play with that threshold as you want, whenever you want, because these ROC curves is actually based on the probabilistic curve. That's why I'm talking about probability now. If your algorithms, anything says less than 0.5, it is my class 0. If it is says anything more than 0.5, it is my class 1. So 0.5 is actually a middle threshold. So class 0, class 1 can be anything. Spam, not spam, yes, no, anything according to your data set. But it is like we know, it is working on a binary problem statement, right? 1 or 0. That's why AUC ROC curve, whenever you have multi-class classification problem statements, there are multiple AUC ROC curve. There cannot be a single AUC ROC curve for 3 classes, right? It works as 1 versus rest, right? So if it is class 1, class 2, class 3, then class 1 versus rest, single AUC ROC curve. Now, how it is plotted? It is plotted as TPR and FPR. TPR is called true positive rate. FPR is false positive rate. So TPR, my true positive rate says true positive will be on x-axis and true positive rate will be on y-axis and false positive rate will be on x-axis. So true positive rate is actually the recall of your system, and recall is sometimes also called sensitivity. True positive upon true positive plus false negative. And false positive rate, as you say, the false positive rate of your system is false positive plus true negative, right? So these are the mathematical imputations of what is true positive rate, what is false positive rate. But now we'll try to understand why this AUC ROC curve is plotted for classification algorithms. It's quite important, right? Whenever we have I'm just skipping this in order to understand this. So this is the ROC curve, guys. On x-axis, there is a false positive rate. On y-axis, there is true positive rate. So as soon as you plot this, false positive rate says the false positive rate of your system, because exactly what it is doing is false positive upon false positive plus true negative, right? So whatever your models are doing bad at the prediction. True positive is a perfect thing, right? The recall of your system. According to this curve, whatever curve is plotted is called an ROC curve, receiver operating characteristics curve, right? So why I've plotted 4 curves. The dash is the baseline exactly, and as the curve goes more to the true positive on the y-axis, the better it becomes. Now it has been labeled as the best one is 0.98. That is the darker green curve, right? Why? Because it is approaching more towards true positive rate and less towards false positive rate. What I mean by this is, and how exactly this is plotted, guys, we take various thresholds. So between 0 to 1, let's take it as 0.2, 0.4, 0.6, 0.8, and 1. Taking down various thresholds and now trying to decide for every threshold, calculate true positive rate and false positive rate. As easy as that. So for every threshold, we will draw a confusion matrix, calculate the value of true positive rate, false positive rate, and plot it here. Then again a threshold. So there will be few data points, right? For 0.2, 0.4, 0.6, 0.8, 1. You have 5 data points. Now you join those 5 data points and this ROC curve comes. It's not difficult, right? Here you need to only X value will be true positive rate value, Y will be false positive rate. How multiple values are generated? They are based on your threshold. So for every threshold, you draw a confusion matrix, you calculate these terms, and you plot it here. So in this graph, the perfect, I would say the ROC curve is the more towards true positive rate. Why? Because here the true positive is a higher value, guys. Why? Because you want your true positive rate to be good, right? Your model is doing good with a positive class, and false positive should be as less as possible. So that's why whenever it will be as less as possible, true positive will be high. The value will be in the top right corner, sorry, top left corner, guys. The top left corner is the perfect value that says higher true positive rate and lower. So the ideal scenario you have to maximize your true positive rate and minimize the false positive rate. That's how you understand a simple AUC and ROC curve, right? So I think we are also running out on time. So let's try to now understand the log loss curve, I would say. Okay.
Anuj, sorry to interrupt. Uh,
Yes.
to all the audience, before we proceed to answer your questions, I would like to request the attendants to please fill in the poll about feedback, as it helps us to connect more such sections. Yeah, Anuj, you can continue.
Okay, yeah, fine. So third metric, guys, is a log loss metric, right? Log loss. Now, log loss or cross entropy loss. You must have heard about cross entropy loss and log loss. It's a certain formula, but we'll try to understand the significance of this formula, right? So it's log loss is actually telling you the performance of an classifier. Again, evaluation metrics, but where to consider, I would tell you. But try to understand how this is calculated. Now, we know that output is a probability value, right? Output is again every time now and then it is a probability value, and try to associate probability to a label, right? Less than 0.50, more than 0.51. Now this 0.5 can be 0.8, then you are becoming very harsh on your positive label, right? Your model should be very confident in predicting, okay, it is a positive class. That's why it's taken down as true positive. So that's how it works, evaluating the performance of a classifier. Now, what log loss does here? So log loss has a tendency where if your label is 1 and if your model is predicting the value close to 1, then it will not penalize. But if your label is 1 and the model is predicting it with certain lower probability, it will penalize it. What I mean by penalize it, it will say, okay, the model is not going good. Why? Because for a label of 1, the probability should be greater than 0.4 or closer to 1, but it is predicting it as 0.4, or even if it is predicting the 0.6, your model is not very confident. Fine. That's why it actually penalizes. In the similar way, if your class is 0, your actual label is 0, but your model is predicting the 0 classes with 0.5 probability, it is confused. It will penalize that. It will add to the loss of your classification system that, okay, actual class was 0, but why? But model is predicting it with 0.5 probability. That understand it. Your model is not doing good. It should actually improve. Right. That's why log loss is a metric that you will often find using in deep learning system for actually optimizing the weights of neural networks and more deeper networks where you want to use actually a function that would optimize your complete system, right? You can actually calculate the log loss of classification algorithm also, but it's basically the goal of any machine learning model is to minimize this value. So the lower the log loss, because it's a loss function, like the lower the loss, the better is your model. Now, before even coming to the formula, just understand it is -1 by n. Just forget this, why we are doing negative and average. Try to understand it that why log of pi 1 minus ya log of 1 minus pi. Now here pi is the probability value, ya is the actual value. So suppose my actual value is, guys, 1. Now the second term will be 0, 1 minus 1, almost 0. You are left out with the single term, right? The first value. If your actual value is 0, then your first term becomes 0. Then you are left out with some. That's why it's in summation of 2 terms. So for yi is equals to, for your actual value 1, the first part is significant. For your actual value 0, the second part becomes significant, right? So if I'll be telling you in terms of graphs, for a value of 1, this is a probability or your log loss graph, where just by the curve you can see if your predicted probability becomes closer to 1, your log loss is smaller. If your predicted probability of a classification system is actually uh, farther than 1, you're actually predicting down the true label as 0.2, your log loss increases. That's why lower the probability closer to 1, the more the log loss. And similar for the use cases of 0, right? For a predicted probability closer to 0, your log loss is 0. But as soon as, if your class label, actual label is 0, and you're predicting it with very higher probability, because that probability will actually correspond to the another label, so your log loss increases. That's why it is actually penalizing your system in a very harsh way, that okay, you have to accumulate this log, and then you have to minimize this log. That's why it's actually a perfect example. And why we do, like, guys, -1 by, we are averaging over n sample. So every sample it is calculated. And why minus? Because whenever you do log, you have negative values. So that's why your total loss should come out it as positive value. That's why it -1 by n, averaging the complete loss over all of the samples. And negative sign is for actually negating down the negative value that comes out of your log. So that's why your log loss is actually a perfect metric whenever you're trying to optimize any classification model. So now I guess we'll go to some hands-on if we have some time, and I will try to actually show you how these metrics are actually there. So suppose, so here, just consider I've taken down a data set called Iris. It's actually a famous data set, the flower data set. It's 3 classes, flower 1, flower 2, flower 3. Just consider it. There are 50-50 samples. It's quite a balanced data, right? I've applied a algorithm called support vector classifier, but here the algorithm is a black box for you. Just need to focus upon confusion matrix, right? So here is a confusion matrix, guys. Here it will be a more than 2 classes. So as I show you on the slide, that was a binary classification confusion matrix, but this is for more than 2 classes. Now, the question should be, if the classes would be more, this would become a very broader picture, you can say, difficult to understand. That's why whenever I talked about precision recall and F1 score, I talked about in terms of binary. So guys, for every you can say, for every multi-class classification, there are 3 kind of approaches to actually calculate precision recall and F1 score. Why those 3 ways are given? Just because your confusion matrix, as I told you, precision recall operates in a way that it should be binary, right? Your true positive and false positive, this should be singular figure. But here, if I say that, okay, my flower is actual flower 1 and predicted flower 1, this is true positive, but what will be the false positive? It has more than one column, so more than one row. So that's why in a multi-class, we take for every class 1 versus rest. So for flower 1, it will be flower 1 versus rest. For flower 2, it will be flower 2 versus rest, and flower 3 versus. So there will be 3 confusion matrices plotted. This is a single, it can be broken down into 3 confusion matrices, so as to calculate precision recall and F1 score separately. So guys, for multi-class, as I told, there are 3 approaches. I have used macro here. So this average terms tells you which technique you need to follow. So there are 3 kinds of technique: macro, micro, and weighted. Macro says you need to just calculate precision, any valuation metrics as a single entity for 3 cases. As it was a 3-class classification, right? I calculated 3 confusion matrices. I calculated 3 precision value. And in last, it would be P1 plus P2 plus P3 by 3. Simply averaging the precision of each and every class versus the rest. Why? Because macro says it's actually, I have to give equal weight to each class. So even if one class has less sample, but it will be important in determining the final metric. That's why it's P1 plus P2 plus P3 by 3, simply averaging. So macro in recall also, in F1 score also, it works the same. Coming back to the micro, what micro says? Micro says my each sample is important, guys. So now it will be not, actually there will be 3 confusion matrices, but instead of calculating precision for 3 and averaging, it will be having true positive out of 3 confusion matrices, and then having false positive, and then summing. So it will be true positive 1, true positive 2, true positive 3. Numerator will be 3, this entity out of 3 confusion matrices, and the denominator will be true positive 1 plus false positive 1. In addition to this, 2 positive 2 plus false positive 2 of the second system, of the third system. So 3 confusion matrices, adding single entity, not simply averaging. This gives equal weights to each of the sample. So this is also approach where people follow micro. And weighted, as by the name it suggests. It gives weightage according to the sample. So by three classes, as I said, one has 20, one has 40, and the other has 40. So it will be giving weightage according to the number of samples. So in average, you can type down macro, micro weighted. It will give down precision, recall, and F1. So that is how in machine, like in Python, you have exactly library, but it is very important for you to understand what is the significance of those library or how these things works. It's as easy as you can say in terms of performing mathematical calculation in a piece of pen and a paper, this library works in the same way, guys. Okay. Now just showing you a
Anuj,
precision.
sorry to
Yes.
interrupt. Since we are running out of the time, I guess we can take some Q&A questions.
Okay, okay, okay. Yeah, just 1 minute. Just is the last thing only. So
Yeah,
this is
sure.
yeah, this is an AOC ROC curve, guys. It looks in the same way for various threshold value. We have plotted true positive rate and false positive rate. So it's 0.903. That means area under the curve. Right. So this ROC curve is this, and this is the area under the. So the more the area, the better your model. Because as I said, more inclined towards true positive. So a perfect AOC would be 1. And the log loss is 0.40. So this value should be minimized, right? The lesser this value, the better is your classification model. So in terms of see Python library, we have functions, but this is how the things are calculated, guys. Now, as requested, we'll be going back to the some of the Q&A. For you guys, if you had any of the questions during the session, as I was unable to take because it's a broader topic. I tried to accumulate it in the 1 hour session, but let's do some hands-on also after this session. You will try to, it will make you actually feel comfortable. Yes, I can take the Q&A now.
Yeah, Anuj, I would be happy to read out the questions for you. The
Yes.
first question is how to minimize FP and FN, false positive and false negative.
Yes, how to minimize FP and FN. So see, guys, if you have plotted any confusion matrix and your FP and FN seems to be um, a very bigger number, right? Your if a false positive is actually big. It depends completely on your data. So suppose you have a data which has a unbalanced, which is quite unbalanced, right? You need to actually provide more samples. So if your negative class has more lesser samples than your positive class, that's why it is not doing justice to your negative class rather than a positive class. So you need to either work out with the data. Second, you can work out with the algorithm also. You can actually play with the hyperparameters like any algorithm. If I would book let's pick up logistic regression, right? You can play out with the regularization parameter. These regularization parameter actually helps you in order to optimize your algorithm in such a way that those false positive and false negative will come down to the lesser figure. So dealing with the data first thing is, and dealing with the hyperparameters, and the third thing also can be whatever input you are giving out to the system, some more information it needs. So working out with the feature engineering techniques, right? If you have a data set where the dimension is very large, you can actually reduce the dimension, see how much variance is covered, and then provide it to the algorithm. So there are multiple things you need to actually, it's a hit and trial approach only. You need to try it down, which is working in your favor, right? So after every approach, you need to calculate the precision and recall or your false positive and false negative, then see which approach is working fine, but it works in the same way, working out with data or the hyperparameters of the algorithm. Yes, and any other question?
Yeah, since we are dealing with values less than 1, log values will be negative.
Yes, definitely. See, guys, it will be a smaller entity in the log loss, right? 1 minus 0.2, 0.3 as their probabilistic value. As your value will be smaller, your log loss, whatever it will be calculated, it will be negative. That's why whenever you calculate log loss, it is minus 1 by n, right? Summing over all the values and then negating this negative sign in order to keep your log loss in a positive direction, right? So that it is actually you can understand it between like the smaller the log loss, 0, it comes down at value between 0 to 1. That's why the negative sign is there in order to cater down the negative sign that comes out of the log you do for this value. Yes. Yeah. And any other questions?
Yeah, that's it. Uh,
Okay.
Thanks a lot, Anuj Dhoundiyal, on behalf of Analytics Vidya. I would like to thank you for your time and for delivering such a wonderful session. Personally, I loved the way you explained the confusion matrix, which was short and crisp. No more confusion when it comes to confusion of matrix.
Yeah, that's the main thing. I want guys to understand like it's name as a confusion matrix, but it's quite easy.
I'm sure our audience found it insightful and hopeful we can connect more such sessions with you in future.
Yeah, definitely, guys. Have a wonderful day ahead, and keep the learning curve on. Keep the practice. Those things are easy. It only requires time and your enough time to in order to understand those metrics. Yeah.
Uh, I hope you guys have filled the feedback poll. If not, I request you to please fill in the poll about feedback as it helps us to connect more such sessions. Then if you wish to conduct a webinar or facing difficulty in registration, please connect all the links which are being provided in the webinar chat link. Even the recording of the session will be available on our YouTube channel. We will be back with another data section of DataHour on 19 January. The link is in the chat section. Till then, bye bye and keep learning. Once
Thanks a
again,
lot.
thanks, Anuj.
Yeah. Thanks. Thanks, team.